Hey guys, it's Miss Hernandez again. We are working on Thursday, September the 24th, also known as 2.5 States of Matter. Um, so let's just jump right in. All right. So the first thing that they put up for us is a question with three pictures. Why is the state of matter different in each picture? And let's analyze what we're looking at. So here it looks like we have a glacier. Here we got a beach with water flowing up the beach. Up into shore. Sorry, I blanked out. And then here you have a volcano with a bunch of snow that's probably changing that snow into vapor, water vapor to be exact. Okay, and probably it's raining somewhere around here if there's any, you know. So why is water in the solid state in the glacier? Why is it in the liquid state at the beach? And why is it water vapor in the volcano? So I want you to take a think for a little bit. I want you to remember what we talked about when it came to the Celsius scale and the different temperatures that water changes at. Okay, I'll give you a couple seconds. Okay, I think that's enough. And you can read here that it's all about the temperature change, okay? And water is one of those unique substances that we can easily change different forms, right? So on the left picture right here, the glacier, we know that the temperature is really, really cold. It's probably about below 0 degrees Celsius. The middle picture of the beach is probably somewhere between 0 Celsius and 100 Celsius, and then it looks actually pretty like warm. I don't know, but it's really sunny, so I'm pretty sure it's at a pretty like normal temperature. I would say 80s or 90s. I don't know, but that's just me. Here we have a volcano. Now it's probably really hot in that volcano. That's how come all of this snow is starting to vaporize because of the heat coming out. All right, so definitely at least 100 degrees Celsius. That's how come we see so much water vapor being released. Now, all of these three are examples of your states of matter. The glacier is the solid, the beach water is your liquid, and the water vapor coming out of the volcano is your gas examples. All right. The state a given substance exhibits is also called a physical property. Now, remember, physical property, what it is what it looks like has changed, not the exact substance. Okay. The only thing that has happened is that you probably have changed the temperature and it went from being a solid to a liquid to a gas, depending on what substance you're using. Now, let's talk about substances at room temperature. Room temperature means exactly the temperature that you're sitting in right now. Some compounds and elements are oxygen and carbon dioxide. Oxygen and carbon dioxide will exist as gas if you're here in your room. Examples of a liquid would be water and mercury metal. Okay, mercury metal is one of those unique metals that is liquid at room temperature. Most metals are solids at this temperature. Okay. Um, all substances can exist in any of these three states, depending on what temperature you have your substances in. There is a fourth matter, and I've highlighted it here in blue. It's called plasma, but we're not really going to study it because it doesn't naturally occur on our world in on Earth. Okay, but there is a fourth state, and it's usually man-made. So the first state we're going to talk about is the liquid state. Again, this is all review. Liquids, you should know, have no definite shape. Okay, liquids will take up the shape of whatever container you have it in. If it's in a cup, it'll look like a cup. If it's in a bottle, it'll take the shape of a bottle, so on and so on. The thing with liquids, if you have a liter of cola and you share it among your 5 friends and you take out a cup and before they drink it, it's still 1 liter total. Okay. The volume will not change. You just have separated your volume. When it comes to particles, you always want to remember still have a certain attraction to each other. But what do they look like as they're sitting in your water or whatever liquid you have in front of you? Now, what is happening? What I always like to think about is like marbles. Okay, if you have a cup full of marbles, they're kind of like no organization. They're kind of just sitting on top of each other. Um, Technically, the particles in the liquid can move over each other, but for the most part, you can think of it as a cup with marbles, okay? And those marbles will represent your liquid. All right. There's not a lot of space between those particles because they're packed so closely. So you can't really compress them and make that liquid smaller. It's really, really hard. Again, we're gonna go back to Mercury because Mercury is considered an anomaly because the way it acts. Okay, but first, a property that most or all liquids exhibit is gonna be known as surface tension. Okay, surface tension is the ability for liquid particles to stick to each other. Are they bonded? No, they're kind of like taped together. And what do I mean by surface tension is look at this picture right here of Mercury. You'll notice that these particles have kind of stuck together to form these giant bubbles. Do we have small bubbles? Yeah, we got small bubbles. You can see them here. The reason why it bubbles up is because of that surface tension between our particles in this substance, in this case, mercury. You have probably also seen it on one of those days, and lately it seems like it hasn't stopped raining, right? Anytime you're driving in your car and it starts to rain, you'll notice all these little bubbles of water start, sticking to your windshield, right? And eventually those bubbles get so big that it forces that gravity forces that water to flow down your windshield. Okay. Ooh, again, talking about that special substance known as mercury. If you were to heat up liquid mercury to its boiling point, which is extremely high, look at that, 357 degrees Celsius, and you have enough pressure, you will notice that that liquid can go straight into the gas state. And I'm talking about all the particles, okay? It's not like water that'll go little by little by little. No. As soon as you reach 357, if you have enough pressure on that liquid, poof, it's gone. It's kind of like a disappearing act, right? 1 minute it's there, and another second it's gone. Gases, you have to remember, have no definite shape. It'll take the shape of its container, and no definite volume because it will take the shape of its container. All right. Particles move in random motions with little or no attraction to each other. What do we mean by that? Well, if you've ever seen kindergartners running around in recess, but you take them out of recess and you put them in a box or you put them in this room. So what's going to happen is that those kindergartners are going to be jumping, running into the wall, running into each other and bouncing off each other. Okay. But imagine if these kindergartners can, run from the floor to the ceiling, to the corner, to the other corner, into each other. That is what these particles look like. And we're going to see a video where you see the movement of these particles. Okay, so if you're a little confused, don't worry about it. There is a lot of space between these particles So as far as compressing the gas, compressing gases, yes, that is pretty much the only one that can be compressed because of all that space between those bouncing particles. All right. And we can basically force any gas with enough pressure into just about any container. Solids is our last state of matter. How do you know that something is a solid? Well, look at the pen that's in your hand. Look at the computer or the screen that you're looking at, or tablet, or iPhone, or cell phone. You'll notice that it's a solid because it has a definite shape, and usually, most of the time, it's really hard. I'm not saying all solids are hard. There's some solids that are a lot weaker and can easily be shaped differently, and it will have a definite volume, right? This guy will have a definite volume. And the particles, you have to remember, they're going to be doing some slight vibrations, right? It's not enough of vibration that you can feel it when it's in your hand, but there is still a vibration between those bonds. And because those bonds are holding on so tightly, it's kind of like, very, very slight vibration, okay? Not enough that we could feel it when we touch solid materials, okay? But we know because of science that those particles are moving, okay? Now, again, going back to that special substance, mercury. So, you know how we said it can go from a liquid to a gas at exactly 357 degrees Celsius? Well, if we have liquid mercury and we change the temperature to negative 39 degrees Celsius, that liquid mercury will all turn to solid, okay? Every single particle. I think somebody should do like a video on that because I would love to see it. Wouldn't that be cool? All right, so we got a short video to do. It's only about 2 minutes long. And here we go.
States of matter. In this video, you are going to learn what the 3 states of matter are, some examples of each state of matter, the characteristic properties of the 3 states of matter. The 3 states of matter are solid, liquid, and gas.
All right, I want to stop it real quick right here because I want to talk about organization and organization for these particles. So, which one would you say is the most organized? Well, if you look here at this solid, you'll notice that all these particles are perfectly lined up in a 3x3 matrix. Okay, there is nothing out of order. Everybody has its own place, and they're probably bonds that are holding these particles together, okay? That's what makes solid so rigid. That's what keeps its volume and keeps its shape. Now, if we're talking about something that is less organized, we're talking about a liquid. In this case, there is no organization. They're kind of just floating around, sitting on top of each other. But if you look at a gas, in this picture, you can't really see it, but these particles, like I said, are bouncing off each other and off the surface of this container. And I'm really surprised they didn't at least put a top on it. Gases don't stay in cups without being sealed or containers. So that's kind of dumb.
Let us look at solids. An example of a solid is your computer. The properties of solids depend on how the particles in solids are packed. In a solid, the particles are closely packed in fixed positions and cannot move anywhere. So, solids are rigid, cannot be squashed or compressed, have a fixed shape and a fixed volume.
Remember, it cannot be compressed because there is no extra room in between those particles like there are in a gas.
They cannot flow. Now let us look at liquids. An example of a liquid is water. Just as with solids, the properties of liquids depend on how the particles in liquids are packed. In a liquid, the particles are again closely packed, but not as closely packed as in solids. So this means the particles in liquids can move around each other. So, liquids are not rigid, but because their particles are closely packed as in solids, They cannot be squashed or compressed.
Again, there's not enough space in between those particles in order to compress that liquid.
They do not have a fixed shape, but they do have a fixed volume. Beware with that one, as many students think because liquids do not have a fixed shape, they do not have a fixed volume either. But they are wrong. If someone orders a pint of beer, they cannot make it 2 pints by pouring it into different containers. As you know, liquids can flow.
Now, flow, like for water. There's another word that we use in chemistry for flowing, liquids that flow, meaning that can be poured, in and out of things. We call that viscosity. Okay. Now, what viscosity, if you have something like water that can easily transfer from one cup to another, we're going to say it's got a low viscosity. Okay. It can easily flow from one container to the other. Now, if you have a substance or a liquid that has high viscosity, you have, for example, something that moves really, really slow, honey, right? When you're waiting for honey to pour out, man, your hand can get tired because honey is really, really thick. Okay, so those particles move and roll over each other really, really slow compared to water. Another example, syrup. A second example, or a third example would be that tamarindo that you guys eat. It can move really, really slow compared to water, especially when you're transferring it from one substance to another, or from one cup to another. My bad.
Finally, let us look at gases. An example of a gas is helium. This is the gas in party balloons because it is less dense than air and unreactive. Again, as with solids and liquids, the properties of gases depend on how the particles in gases are packed. Unlike solids and liquids, the particles in gases are not closely packed. They're far apart. As a result, gases are not rigid and can be squashed or compressed.
The reason why it can compress is, remember, it used to have a bunch of space in between these particles, and you just put enough pressure and you can compress easily any gas.
Do not have a fixed shape nor fixed volume. They fill the whole space they are in.
Alrighty, good one. All right, so we have a second video that we're going to watch. I know it's really, really old, but it's got some really, really cool ideas. So bear with me.
When a solid gets warm enough, it melts. To explain what's happening, imagine you can see how the particles in a solid are arranged.
Did you see that vibration? That vibration is happening, but it's not enough of a vibration that it's breaking the bonds that hold this solid together.
They're in a fixed framework, vibrating but not straying far from their main position. When energy is supplied,
energy in the form of heat, the more heat that you apply, the more these particles start to move, and the more they start to move so much that those bonds that are holding the particles together start to break.
The particles vibrate more violently and become free to move. The solid changes into a liquid. Melting involves a transfer of energy. This can be
transfers of energy usually is happening from the environment around that substance into the substance. Okay, so the heat goes from what's in the air, whatever heat is in the air, into the substance, and that's what's causing that change of state.
Illustrated by putting an ice cube in a sealed container, leaving another one empty. The air on the left is at 25.5 degrees Celsius. As the ice melts, it takes energy from the surroundings.
Look at that.
The temperature temperature of the air in the right-hand container has fallen by about 3 degrees. Energy is also needed to change a liquid to a gas. So, what's happening to the particles this time? In a liquid, the particles...
So, remember that marble bag that we were talking about? If this is a cup, this whole square is a cup, you'll notice that all of your particles are all your marbles are sitting at the bottom of your container. There's no organization. They're kind of just like sitting on top of each other. Very little space between these particles. And they can move, okay? They can roll over each other and move around the container, especially when heat is being applied. Watch.
Particles are free to move around. Heating causes them to move around more quickly. Those which have enough energy escape from the liquid, forming a gas. This is evaporation. Ether evaporates at room temperature. It's taking energy from the surroundings and disappears in less than 5 minutes. It's possible to see how different liquids take heat from their surroundings using thermometers wrapped in string. They all start off at room temperature. The string absorbs the liquids. Number 1 on the left is a control. Number 2 is dipped into water, 3 into ethanol, and 4 into ether. As soon as the string leaves the liquid, evaporation gets underway.
What's a liquid? It's changing into a gas. It's absorbing the heat that's in the environment.
The temperature of thermometers 3 and 4 quickly begins to drop. As the liquids evaporate, they're taking energy from the string, the air, and even the bulb of the thermometer. So, which has taken most energy from its surroundings? Liquid 2, 3, or 4? Gases can also be changed into liquids. For this to happen, they need to be cooled. Liquid nitrogen is extremely cold. Immerse a balloon full of air in it and see what happens. The balloon shrinks and becomes brittle. Inside, you can see a liquid. It's liquid air. This time, the balloon is filled with carbon dioxide gas.
Do you think, like, because the balloon is so big,
nitrogen, and
you would think that since the balloon is so big, there's a lot of gas particles? Check out actually how much it has.
Cools rapidly. What's inside the balloon this time? If a gas gets cold enough, it changes into a solid. This is solid carbon dioxide.
Look at how little bit of carbon dioxide was in that big balloon, okay? These gases, even though they're so very little particles, it takes up a lot of space, especially when with a balloon that could allow it to change, expand to as big as it can. Really, really cool. I want you to watch also how carefully watch those particles, the substance, how it automatically just disappears.
See how it changes back to a gas at room temperature.
Look at it go bye-bye. All right, so that's a neat video. Even though it's super old and the can't see it that well, I think it's a really, really awesome video. All right, so let's summarize what we talked about today. You have the 3 states of matter: solid, liquid, and gas. When it comes to solids, you'll have definite shape, definite volume. Liquids have a definite volume, but the shape will change to whatever container it's in. Gases will change shape and volume, of whatever container that you have placed it in also. Okay. You have these 4 review questions to do. They're due today at midnight. How many states of matter are there? We talked about that. What is a solid? What is a liquid? And what is a gas? Okay. All of those are extremely, extremely easy questions. Make sure you get them in as soon as you can. All right. You have a great day and talk tomorrow. Sorry, I paused.